Welcome back.
Okay, I think we decided to do the same exam, part four,
Okay.
the first four questions. They're like draw the stereoisomers and then
Oh,
the
yeah.
orders. And I thought the Ginsbergian one would be good to go over too.
Sure.
Yeah.
All right. Let's see. Acids in order, bases. Let's just do one at a time. Let's do draw all possible stereoisomers coming up. And we haven't shared screen yet. I realized doing that right now. So still on fall 20. And here we go. And so we're drawing cyclopentyl octane. Hey, we're drawing octane first. Forget about cyclopentyl. That's just a group. So octane. So we're going to be drawing either 3 or 4 molecules. The only way we're drawing just 3 is if there's a meso one as one of them. 2, 4, 6, 8. And I'm pretty sure this won't be meso because there's different groups on carbon 3 than 4. There's no bromo on 4, so they're different. So 3,4 dibromo. We'll put a bromo on 3. Put a bromo on 4. We'll put a cyclopentyl on 4. 1, 2, 3, 4, and back for 5. Please, this is all about stereo centers. So if you don't have an H on your stereo center, when the stereo center has an H, that's trouble. So put the H on this stereo center. Please don't put an H on the other stereo center. This won't be a stereo center anymore. It'll be a unicorn with an octet violation. Okay, make life easy for yourself. Make this a dash. Why? Because H is the number 4 group. Choose an adjacent position for the wedge. That's convenient right there. Do yourself a favor and make this the dash. Why? Because that CH2 that has nothing special on it is going to lose to this C with 2 C's, is going to lose to this BR, is going to lose to a C with a BR. All right, and don't forget, you need an adjacent wedge. And do your stereo centers. You got a 1, you got a 4. You've got a 2. Why is that a 2? Because it's a carbon that has a bromine. It's going to beat a carbon without a bromine every day. 1, 2, 3 is S. Other stereo center. Go for more contrast here. Hot pink. 1 for a BR. 2 for a carbon with a BR. 3 for a carbon that has 2 carbons. And 4 for a carbon that has 1 carbon. So the second thing you're comparing is the second bond to carbon here with an H down here. This one's also S. And my strategy is to draw the RR version of this molecule. And the easiest way for me to do that, although this is not the only way, is to put a pretend mirror on the page and draw away from the mirror the same distance, coming up to a dash. And there, away from, away from the mirror. And and what about that wedge? The wedge has to come off. 1, 2, 3, 4, 5th carbon away from the mirror. 1, 2, 3, 4, 5th carbon away, and it's towards the mirror and a little bit up. And it's a cyclopentyl. And the BR is definitely away from the mirror and up. The H on the next carbon is down and towards the mirror. The BR on the same carbon is down and away from the mirror. You have successfully drawn the mirror image, so doing the stereocenters is easy when you have done that. The pink S is now a pink R across the mirror. The green S is now a green R across from the mirror. And I'm not going to do any computer cheating that the teacher can do during lecture. I'm going to start with my strategy and start from scratch. I want to draw, clearly these are enantiomers. I want to draw a diastereomer of this one. So I'm going to copy everything as is. And I'm going to keep the stereocenter up here exactly as is. So no change on that one. And I'll just do a single switch down here. The BR got replaced by H and that's a single switch on an S stereocenter. Always creates R. No change on the pink S. Still pink S. And when I draw the mirror image, pink S will become pink R. Wow, I thought I had a new pen that was better. Oh, if I hold it on the screen, it does a function that I didn't know existed, apparently. And I lost track of where I was. There. 2, 4, 6, 8. Okay, fifth carbon in from the mirror. 1, 2, 3, 4, 5 has a wedge. 1, 2, 3, 4, 5 has a wedge sticking towards the mirror and up. And the BR there. Now on a dash on the next carbon away from the mirror is a BR dashing towards the mirror and down. Wedge away from the mirror. Don't hold it on the screen. And the pink S mirror image is now pink R. The green R mirror image is now green S. There we go. These two are also enantiomers. And let's go back to our earlier Q&A question from today. How do you know these are diastereomers? The green stereocenter changed and the pink one stayed the same. That is diastereomers. Same story here. The pink one stayed the same and the green one changed. Oh, the green one changed in both. And how about going from here to here? Careful, use the colors. Green S stayed green S. Pink R, pink S1's different, so they're diastereomers too. Just like color change here. Just so you know, this arrow, pink S, pink R, green R, green R. R's green stayed the same, pink changed, also diastereomers. And after you did that hard work on the first molecule for your first 3 points, the other 15 came rather quickly after that. Good one? Any questions on this before we go to question 2 from the same exam? Once again, we're doing fall 20 big time today. And part 4. All right, question 2 coming up. Question 2, we're going to put explain your choice. Yeah, that's good stuff. Oh, I undid something. I hit that goofy. Okay, fall 20. T2, part 4, continued. Okay. We can always start these with our pKa's, and then we have to use some trends on the periodic table occasionally, especially when I see phosphorus. You start freaking out on me now because, oh, he didn't make us learn anything with phosphorus in it. What's he doing? Or some of you are saying, oh, that's that new phenyl group. Oh, no. Oh, don't do that. That is not a phenyl group. Some of you learned the hard way on test 1. You are not allowed to make mistakes of lowercase and uppercase in this course. People have died for less. Somebody trying to make a pretty cobalt jewelry item instead gets carbon monoxide poisoning because you made the little o into a big O. That comment is on somebody's test, so it's no laughing matter. pKa's here. 10 for an ammonium. 40 for an amine. They are not even in the same ballpark. When this loses a proton, it becomes a neutral amine, which is really stable. When this loses a proton, it becomes a nitrogen anion, which is not stable at all. Okay. Now, I don't know the number for this, but on my periodic table in group 5, I have nitrogen up here and phosphorus right below it. And remember the trend in acidity as you go from NH to pH is to get more acidic as you go down, because the conjugate bases you're making are larger ions, or yeah, in this case, a larger ion, which is more stable. Okay, so I don't need a number. I just need to know it's roughly 10, but a little less. That's all I need to know for this question. And this is an alcohol here. I'd like to say 17 to 18, like the number you're memorizing, but I'd also like to point out there are 2 alcohols where the pKa is closer to 16. You don't have to know that, but I can't in good conscience as an organic chemist put 17 for ethanol when I know full well it's 16. Go ahead, put 17 there, you're going to get full credit. In fact, the numbers really don't get credit here. It's putting them in order that gets credit anyway. So the 17 would do you fine for this problem. What is the lowest number on the page? Less than 10. So that is the strongest acid, and I want the weakest first. So Roman numeral 3 is last, and then the 10 is next, and then the 16 is next, and the weakest is this. And I'll just say N minus is the conjugate base. This is minus H plus in this reaction. Very unstable is part of my answer, because I'm comparing that to this, which becomes N neutral. Let's just write this Z. N neutral. You want to go Lewis? So you got 2 lone pairs to make a minus. More stable. And show me that you're using the stability argument to compare those 2 things. Just there. That says it to me. It's easier to make a more stable species than this, so it's going to be easier to take the proton off this one than that one. And this one, where are we going here?
You have it written differently on the key.
I do, because you know why? I wasn't talking about the molecules I'm showing. I got the 2's there, it goes to N minus. And then the 4 is not, it's not that one. It's not that one. It's this one. Yeah, probably just I described it a different way, but I was really describing the same thing. I just want to make sure I was 4 wasn't the N becoming N neutral. 1 was the N becoming N neutral. So it went from NH3 plus to N neutral. And so that's the comparison there. 4, we're going to an O minus instead of an N minus.
You have on the key that's 2, 3, 4, 1.
Ooh, 2, 3, 4, 2, 3, 2, 3, 2, 3, 2. Oh, in my mind, I had P with a plus charge, didn't I? I lost my mind here. Look, this should be similar to this. I mean, look how similar they are. Why was I?
Yeah, so
In my
should it
mind, I
be like
started here, right? So yeah. Sorry, I'm glad somebody's paying attention here. Okay, so it's close to 40, right? But it's a little less than 40 for this argument with this argument here. I started in the wrong ballpark. Yeah, don't compare. I was to put the less than 10 there. I was saying a P neutral is being compared to an N positive. No, they're fundamentally different. P neutral and N neutral are almost the same as they were laid on the periodic table, yet the size of P becoming P minus, and that does change the order of things. I almost want to start the video over, but let's see if we can recover here. I'll retrofit it later. What do we got? O minus is going to be a lot more stable than N minus, and that's a trend on the periodic table based on electronegativity. If you're comparing O minus to N minus, it's easier to make that O minus because it's more electronegative. More electronegative. Oh, wow, that's not working at all. Huh. Okay. I guess that E is being used twice. More dectroneg. Let's try it one more time. E L E C T R O N E G. And I won't write the G. Okay. So the question is now 3 is way out of position. It's in the ballpark of 2, but a little better. All right. So the 2's staying there. I just need a little room beside it. Is that what I had on the key?
Yep.
Okay. And now we just got to describe why 3 is a little worse than 2, or better than 2. And we did that here, over here, because I'll just do it up here since I started over here. 3 is better than 2. Because it makes a larger, more stable anion. Anions are most sensitive to size, and size changes as you go up and down on the periodic table, not so much when you go left to right. So I think I did that, recovered somewhat okay. Not the cleanest video, but even the mistakes are educational, right? So answer key might be a little clearer for you to work from. And we wanted to do number 3 as well. And here we go. Place the following order of increasing base strength. I have to flip the script here. All right, so I'm going to draw the conjugate acids under here. C Amazing. CA. This, don't forget. Everybody's got a spectator here that's irrelevant in this question. And this is CH3CO2H. What's the pKa of the acid? 5, so the pKb equals 14 minus 5. Wild. It's going to erase everything. Nine. And this is the conjugate base of an alcohol. I'm going to go stick figures now. Put the H's in black. And, you know, you can write 17. I don't mind. And I'm going to put 16 because that's closer to reality. pKb. I'm going to stop showing my work now. -2, 14 minus 16. pKa of 2-fluoroethanol. Don't worry about its name. It's the species here. There's something called the inductive effect I hope you've read about. It says pKa is going to be close to 16, but less. And this looks almost exactly like toluene sulfonic acid. And that one we have to know has a pKa of -5. This one's benzene sulfonic acid. It's just one methyl short on the phenyl of toluene sulfonic acid, which doesn't change the pKa hardly at all, less than 0.1, I believe. pKa -5. -5. So that's our strongest. I'm going to go largest numbers weakest first. 2. 16 is larger than less than 16. 3 is larger than 5. Is larger than -5. Explain my choice. Well, you can use stability of the bases as your argument. This is a highly stabilized by resonance. You don't even have to show me that. Just know that the reason why toluene sulfonic acid or benzene sulfonic acid is such a strong acid is the base is really stable. Stabilized by resonance. And then this one is stabilized by an inductive effect when we're comparing these two. O- stabilized by inductive effect. And now we're comparing, oh, well, compare 1 to 1 is over here. It's going to be better than any alcohol because it's stabilized by resonance. Notice I didn't use the word highly stabilized by resonance, which implies that it's not as good as this one because it doesn't have quite as much resonance. But it makes it better than the other two. And I hope that did a good job for that one. Do you want to save? I think I got to move it down for number 4. No, Ginsbergium. Fine lady. Here she comes. And do a buffer problem. All right, so we're going to start with some fictitious acid. Some fictitious acid. And we're going to talk about this one, which has 4 pKa's. So before I even start, I don't even read this question when I realize this is the buffer problem, because it'll have this exact same words. It'll end with no calculator show work. I'll change the name here. I'll change these numbers. You don't know how many numbers I'm going to give you. When I give you 4, you need to know that the first number is for when all 4 protons are there. Call it H4A. You want to go G for respect for Miss Ginsburg? There you go, H4G. The next one, next lowest number is the next strongest. That's H3G negative. And the next one would be H2G2 negative. This work is not time wasted. It's going to help you finish this problem quickly. And this is the last pK, so there can only be 1 proton left. Hg3 minus. All right. So I will be telling you how many protons are there from the start. This is the time where I don't want you to go back as far as you can in old tests. I used to be a hard ass on this, and I'd say, like, instead of monoprotonated, I'd say try sodium Ginsbergium. Then you'd have to figure out, oh, the sodiums took the place of the H's and there's only 1 H left. No, I'm going to use these words. You want to hear the 5 choices that can be this word? Here's one of them: monoprotonated. The next one, diprotonated. Next one, triprotonated. Next one, tetraprotonated. Hey, that's only 4. He said there might be 5. Oh, fully deprotonated. That would be G4 negative, by the way. Those are the 5 choices of words that will be right there on the test. Okay. Okay. Now, if I had 5 pKa's, I'd have 6 choices of words. You're not going to make me explain that, right? All right. So we're starting with the monoprotonated. Which of these has 1 proton? This has 4, this has 3, this has 2, this has 1. That's where you're starting. You're going to do ice problem number 1. You're going to start with Hg3 negative. You're going to add a chemical to it. In this case, it says hydrochloric acid. We need to know hydrochloric acid. I promise you, in this question, it'll be either be hydrochloric acid or sodium hydroxide. And you're not going to flip out on me if I make it potassium hydroxide, are you? I don't even hear the word sodium and potassium anymore when they're spectators. They don't register with me. So what is HCl going to do? Give a proton to Hg3 negative or take a proton off? It's called hydrochloric acid for a reason, because it gives up protons. So you're going to make H2G2 negative, and this, I don't even need to see Cl minus. It's now a spectator. So yeah, who cares? You see on all the old exams, who cares after that? What are we starting with? 2.5 moles of this monoprotonated species. Let's go with purple. And 3.5 moles of HCl. And we didn't start with any of this. And I don't care about Cl. I'm just going to leave it. What does stoichiometry say? We have one of these chemicals, and one of them's limiting. The one that's limiting runs out. This one. It reacts completely. Limiting, I don't know why it became a 2.4. It reacts completely. There's none of it left. This thing, you can't lose more than 2.5. You're left with 1.0. If you're left with either a strong acid, which we have here, or if there was hydroxide left in the other kind of problem where it said sodium hydroxide here, if you had any left like we do here, you're not done. You have to go to the next ice problem. Okay? Here, we're not done. There's going to be one more ice problem because you still have strong acid. What does strong mean? Strong means it has to react. You're not done. Okay, we made Hg3 minus into H2G2 minus. How much? For every mole of this you react, you make a mole of this. For every 2.5 moles of this you react, you make 2.5 of this. All right. So we made 2.5 moles. We're set up for ice problem number 2. There is no more monoprotonated Ginsbergium. It is not relevant in this question anymore. Ice number 2. You're starting with what you just made. H2G negative. 2 negative, sorry. I just copied it. HCl reacts to give H3G negative. H2G negative, how much you got? Well, you said you made 2.5 in the previous problem. That's what you're starting with in this one. You only have 1.0 HCl left. You started with 0 of this. Which one's the limiting now? HCl. What happens to the limiting? It reacts, all of it. You can't react more than 1 mole of this one because there's only 1 mole of HCl. You're left with 1.5 moles of H2G negative. You made 1.5 moles of H3G negative. Is that right? No, you didn't. I've done this before. You can't make 1.5 when you only reacted 1. That's crazy. You reacted 1 mole of this to make 1 mole of this. Oh, it went off the pen mode. I had the eraser on. That was not the pen's fault. I suspect it's never been. All right. We now have what's called a buffer. Do you know how I know we have a buffer? The easy way out is to say, well, it's a buffer problem. The question says so. Resulting buffer solution. Why do we have a buffer solution? We have an acid on the right. Hey, question 1, which of those two is the conjugate acid and which one's the conjugate base? The one with the extra proton is the acid. I know you have pKa's for both, but only one of those pKa's has any relevance in this problem. The pKa for the one that's the acid in this buffer. That work we did earlier, this is the only one in this pair that's the acid. This pK, that's meaningless. It's not an acid in this buffer. It's a base. H3G negative, pKa 4.6. So if you just stopped and wrote down the pH is close to 4.6 because you know the buffers keep pH close to the pKa of the acid in the buffer. Buffers keep pH close to the pKa of the acid in the buffer. That is the most important thing to remember about buffers. You'd get 4 out of 5 points for just saying that. pH is 4.6. But we don't have exactly equal amounts of the acid and its conjugate base. We have a little more of the base. Look, 1.5 is a bigger number than 1.0. So you get another point for saying when there's a little more base than acid, what do bases do to pH? Raise it or lower it? Please don't say bases lower pH. Basic means high pH. Bases raise pH. So pH equals, here, I'll give you full points for just saying this. Not even giving me a number. Well, you gave me 4.6, but you said up. If you wrote for example, 4.7, I'm happy. Don't raise it up very much. Buffers keep pH close to the pKa of the acid in the buffer. That's what buffers do. That's why we're alive, because our blood is buffered and our enzymes are all optimized for that pH. Okay, I'm going on a little too much. Anyway, that was a long segment. I will come back if you have more questions. So if I see you on the other side, this one could take about 8 minutes to render. If I see ya, I see ya.